So with this lecture, what I'll do is actually start to tie in some of the static analysis using IDA Pro, or I keep saying IDA Pro, IDA Free, because this static analysis actually exists in the free version of IDA. So, and then what we'll do is analyze a malware sample that I have to try and see about getting some of the the data at runtime out of it for the different features that it has. So go ahead and look at this. So I believe I might actually have to load it up. So I'll go ahead, I've already got a shared folder set up here. So I'm going to copy over the malware sample that I have in here. So now you can see I have it in there with a whole bunch of the other ones I've been working with during class. So taking this, what I will do is I will also jump over to the Windows VM, I think is this one. Yeah, it's this one that I have set up to try and analyze this. So what we'll start with is give me 1 second. Sorry, do this for a second. It loaded up in like this full screen mode, so I need to actually try and get it minimized. There we go. So let me go and shrink this one down. Sorry about that. There we go. It's just the projector here has like a really, really terribly small resolution. So there we go. Have that up, and then I also have this one up. So, this right here is a copy of the malware sample that I was going to work with. It's one that I found. I think it's an older one. It's based on that DarkComet that I showed everyone during the attack lab. And what we will do is, oops, this is fine. So what we will do is try and run a listener. So I think it's around here somewhere. I put it in here. It's dynamic tools, right? So from the class that we did the dynamic, so when we started with some of the dynamic stuff and the network simulation, all that stuff, you might remember this tool. Oops. And then I also had the iNet Sim tool as well. which is right here. So this should go ahead and for that. So we can test that it's working. Right here. So basically I want to simulate, the internet, so to speak, quote unquote, by having that service listening on my host system. I could have easily also set this up on the Kali Linux system if I wanted to. I just happen to use my host system. The goal of this is that when I run a piece of malware, I want that malware to try and connect out to, I want it to try and do a DNS lookup and then connect out to what it thinks is a server on the internet, when in fact it's going to be connecting to my host system where this tool's running. So I'm going to do one more thing, which is I'm going to also go into the logs here. Want to be able to look at the log. So if I remember correctly, it's service log, right? So now I'm going to go over here and I'm just going to go ahead and test this out. Just to let you know, I did already configure the DNS server to look so this is a default setting. So this is me testing that if I went to bing.com, it's actually being captured by this tool right here. Right? Let me move this so that it's somewhere that's easier to get. And you can see all the, all the stuff right there happened. So what I'm going to do now is so I just started this VM up, which means that it's already set up to, so if I run this piece of malware in it, this might do something. Let's try Wireshark. Up. I don't know why it doesn't distribute that. I have to install the older version of Wireshark. Sorry about this. I don't know why it doesn't distribute the sorry, I thought I had this already set up. Come on. I thought I had this already set up. Working. So, anyhow, let's see. So, I can also go over here. Okay, that's fine. I can go over here to, where is it? The analysis and this thing, sysinternals, and I can look at the process explorer. Basically, I'm going to process explorer, so this one. So this will allow me to see if that program is actually running in the background or not. the one that I installed. It looks like it may or may not be. It might also have to. Anyway. Sorry. Here, Wireshark's installed now. So, let me try this again and see if it works. So now it's working. So now, see if this works. I don't know what this is trying to do, the Microsoft updates and everything. Anyway, tried running the program here. I don't want to do that, I want to do this. So restart it. I'm going to jump into statically analyze. So basically, in a nutshell, I don't entirely know what the program itself does at this moment. So I want to try and use some of the static analysis that we exercised early on to try and see if I can basically learn more about the program in order to try and use it, in order to try and get it to do something in the dynamic side and basically learn some more about it. So I'll do this. Right. This one. Yeah, it's this one, right? Yeah. So, one thing we learned how to do was use kind of obj dump to walk through the different pieces of code, or I should say the different functions that go in to build this program. So I'm going to go down here, and what you can see is that it uses some code to go and look at the registry. Has some code that
user interface, user input.
Yeah, has user input code. Has a handful of other things. Let me just look at this. So, sorry, I was just gonna try and see if this was doing anything over here. But you can see this. It's the load library call as usual. But if I keep going down, what I can see is it actually, has some entry points to hook into mouse events and keyboard events and things like that. I don't know what the deal is with the input on this VM today. But anyway, I'll say that what we're seeing here is customary with a large amount of software that does monitoring of a lot of the Windows UI systems and stuff like that. So it's not entirely what I'm looking for when I'm going, or the piece that I'm trying to zero in on here is this one. So this one is one of the libraries that's used for network connection, network access, stuff like that. And the fact that it uses all these, and in particular has connect and bind and accept and listen, kind of gives some information about that. It might have the ability to open up listeners and also open up listeners and stuff like that. So in addition to trying to connect out to a remote system. So the other thing that's interesting is it has the shell execute A, which is typically used for arbitrarily executing command lines and stuff like that.
And other exe programs. So.
And then URL download to file, so it's got some code built into it to do that. So what I'm doing is I'm kind of identifying, just using static analysis, what different function, Windows API calls are available here. These will be useful for me to
internet.
So there's an internet open. FTP put files, interesting. So that suggests to me that there's some code specifically around that protocol that it's using as well for uploading files. Also has some code related to playing sounds and also reading. You can notice there's a whole bunch of the wave in functions. So that stuff is related to reading data from a microphone source in Windows. So that's API call is useful for that. So kind of the reason I'm highlighting these things, I'm starting to build an idea in my head of the different functionality that this tool seems to implement just based upon the Windows functions that it's calling. So it has some capability for connecting to a network or connecting to something on the network, has using TCP/IP, has the ability for listening for incoming connections as well if I wanted to do that. Has the capability of being able to monitor various UI elements of Windows, which includes mouse events and keyboard events. Has the ability for reading data from microphone. So if I want to learn about any one of those things, I was trying to see if there was maybe one more thing here. No, so that about covers it for this. So knowing those things, now what I can do is I can try, loading it up in, say, let's do this. Loading it up in IDA free and seeing if maybe I can look at the code that is calling those things to get some idea about, say, where that program execution occurs. So while this is loading, because it'll take a little bit, I'm going to jump back here, and I'm going to close out of this version of Wireshark, and then I'm going to power off the machine, restore the current snapshot. I'm going to boot this back up. There we go. I'm going to boot up the Windows machine again. So I'll let IDA Pro. So if you remember, or IDA Free, I'm going to let IDA do its thing, which can take a little while. Let's see, it's still analyzing. So go here, load up Windows. There we go. So let me go and fix that Wireshark issue really quick. Apologies for having to do this in the middle of class, but it only takes like an extra minute or so. Go. Here. And so you can see this one's still analyzing, so that'll take a little bit to do. I will say that this particular malware sample, I believe, has like a number, or I should say, has a lot of different blocks of code. So give it a moment to start up.
Is there a systematic approach to verify that everything we just saw, we just, guess that the malware we're trying to do? Is there a systematic approach to verify every single one of them?
So yes, there is a systematic approach to do it, to try and, if you wanted to exhaustively investigate every single one of those, there's kind of a systematic approach. So I'm going to do a variant of that, as part of the lecture today. One of the complications is that, and as you can see, one of the complications is the size of the code. So I could, if I was to spend every single day for the next month analyzing like this one and trying to just approach it brute force systematic approach, I could easily, maybe get through, maybe only get through like a tenth of it or a fifth of it within like a month's time of heads down analysis. So it's usually kind of a balance of kind of heuristics, like what I did. I looked through the different entry points to try and figure out what this particular malware sample likely did based upon what functions were linked in. My expectation on that is that every single function that is linked in and is connected to a real functional piece of code that gets executed at some point basically has a purpose. So the way that Windows linking works is that if a function is not used, like if an API function in a library is not used by your program, then there won't be a reference to that function. So that's why, for instance, you saw that I think user32.dll actually had two separate entries, and that's because two different components that were linked into the program actually reference that library. So there's one component that I guess handles a lot of the user interface layer stuff, the desktop monitoring piece, and then there's a completely different one that is a little bit more of like the low-level user input functions, or I should say user interface functions. So like the basic stuff that a Windows program would need. So we'll let this keep going. This is done. Let me just save machine state really quick so that I can more easily get back to it. This is a good example of what to do. Try and get the VM up to a nice running state. And so then what I'm going to do is I'm just going to delete this old configured state. That's going to preserve the, let's see, hopefully this doesn't take too long. I don't think it'll take 8 minutes, but no, there it goes. Should be relatively quick. So let's see, what's this one doing? It's still walking along. So, yeah, apologies. I tried to have this one ready, this analysis ready before class, and then for whatever reason, the Kali VM actually crashed while my screen was locked.
Yeah, but when we run the malware in the debugger,
yeah,
we can actually step through every single, step of the code, and then you see all the function call. You get into the function call and see exactly what it's trying to do.
So, so you can do that. The one complication you run into is that most, that's a really good approach to do it, is to run the malware and then step through all the lines of code. Problem is that stepping through all the lines of code can be very time consuming. The other piece is that most malware is designed to, or maybe not most malware, but a lot of malware that you'll encounter is designed to connect out, and then it's expecting remote commands to come in from the other side somewhere, right? So If I just run it and then I let it connect and everything like that, all the code paths that it's running through is just the uncontrolled state, right? It's all the automated stuff. But for instance, say this malware has that code in it to do microphone, to listen on the microphone, right? To turn the microphone on. And then monitor any conversations that happen to be going on in the room. That functionality may only be triggered if the operator on the other side specifically sends the command to turn it on. So if I run it and then I step through all the code, I actually need some method for being able to control from the remote side that basically force the malware to do that sequence of steps, right? I need for it to run through that code path. That's not necessarily something I can do from the debugger unless I have like a controller for the malware. Which in this case I might have one. I'm probably not gonna do that during this class, because like that would be add a third VM and all that stuff, and so that's a little bit kind of outside of the scope. So what I will do is I'm actually gonna take this and I'm gonna run it, start it up in the debugger. And so what it's doing is it's actually analyzing the program to try and figure out what DLLs it needs and all that stuff. So I can go here, and this shows me a list of all of the Windows DLLs that it depends on, that the particular sample links in, including, I forget what red stands for, but I think that means that those aren't loaded yet. So those are like delayed load. Windows has this feature within it, and Linux does too. It's a lot more common for Windows programs to do it because a lot of people tend to try and heavily optimize Windows programs for user, for general average user experience. But the feature is that you can load some libraries at runtime if you want. And so they won't be loaded until the part of code actually that needs to reference them is called. In other cases, you'll have a lot of other DLLs that are hard-coded into the program to get loaded by default as soon as the program's started up, so before any code starts executing. So this is the log file. So I didn't show anyone this, but this is actually really insightful piece of Immunity Debugger. There's actually like a log, if you click on L, I think it's called log, yeah, that actually gives you some updates. So anytime it crashes and stuff like that, or you're running into it crashing repeatedly, you can see what's going on there. So I'll jump back to the CPU window, and let me do this also. Sorry, I'm just trying to align this for how the projector decided to come up today. So this right here is the beginning of the program. So and I'll just say that before I do anything, this is where the program decided that it would start running, right? When I loaded it into the debugger. So ostensibly, this is where Windows is going to start running the program. What I may want to do is try and see if that happens to coincide with, whatever the start function is here. So this right here. So it's 48C, 87C, 48C, 87C. So you'll notice that IDA free ended up evaluating the runtime memory location of this program in the same place. So now I have it up in both places. So I can see the program graph here. And then over here, I can actually see the kind of linear layout of the program. So one of the neat things that I end up realizing about this particular program right off the bat is that this function that it starts off with, where the entry point is, happens to be a really long, like linear sequence of blocks. So you might want to go through here and figure out what the deal is with that, or figure out why that is. So one thing that I start to realize here is that there's these references
Yes.
to strings, and so yeah, it's got these different references to strings. So what I might want to do is I might actually want to just try running the program and hit every single one of the, or at least, yeah, hit every single one of these things to see kind of what's going on, because this is very interesting. This one's kind of a nice one because it builds the stuff out for us. But, you know, I don't know if anyone wants to guess maybe like what's going on with all these things. It's basically a linear sequence of commands where it's loading data in. And then it, you know, so basically what's happening here is it's going to be building up the runtime configuration for the malware. So it's that's coded somewhere in the program, and it may be, you know, this is my guess, it may be trying to load those things into memory somewhere. So what I will do is I'll actually go to about right here. Let's see. Oh, whoops. And I will put a breakpoint. So I'll just put a breakpoint here. So now the program paused right here. And then let's see what happens if I keep going down. I should also show you this right here, right? So this thing says that it's loading in whatever this is, ASCII, PWD. So for those of you in the room that have like the really crummy projector, it says QUE password, like K password or Q password maybe, or something like that.
Is that a query for the password, or?
So in a nutshell, what this is doing is somewhere in memory there is a data structure that has the runtime configuration for this malware built into it. So if you remember, this is as I said, this is a DarkComet variant. So this is the same type of malware as back during the beginning of class. I think it was the second or third week or something. I went through that exercise where we used Metasploit to try and compromise the machine. And then after Metasploit got the initial foothold in the machine, I then built a piece of malware using that GUI tool. And I selected all the different features and everything like that. And then I wrote that into an exe, and then I used Metasploit to load that and run it on the computer, which would then allow me to, you know, to then ditch Metasploit basically. So for instance, if you know, Metasploit is a very commonly known piece of software, generally speaking, it's a lot easier to recognize Metasploit than it is to recognize other pieces of malware that might be a little bit more obscure. So it stands to reason that it's benefit to me to jump over to it. So that tool that I put together, or that I should say, that tool I was using to build that second piece of malware, DarkComet, does not actually come built with a compiler or anything, but it gives you an exe. What it has is it actually has an exe template pre-packaged inside of the tool. So it's got almost like a, you can think of it as like a fill-in-the-blanks exe. And the blanks are all the different configuration options that I can pick and choose. And so each one of those things actually match up with each one of these things. So I can still keep going down. We'll just see that this one, this 548, seems to be the function that's called to retrieve the value after this is provided to it. So it's doing a lookup, right? So I'll keep going down, and I'll go and see maybe what it tries to retrieve for mutex. So what it tried to retrieve for mutex was DC underscore mutex dash Q. So you can see the first one was Q password. This one's DC underscore mutex dash Q. Remember, these were text entry fields. So you're starting to learn is that whoever decided to put this together really likes the word Q, Q-U-E, or K, if you prefer the Spanish. So for whatever reason, they like that word, and they decided to use it all over their malware sample. So we'll go down here to the SID, and then it pulls up QID. So somewhere in there, they have a configuration block buried that is talking about these things. And it seems that this function, this 48B548, just based on my observation, is the function used for retrieving all these things. Now this context isn't something that I understand naturally by just diving in with IDA free. Because in order to understand that that's what's going on here, or I should say in order to verify that that's what's going on here, I actually need to run the program and see what the inputs are and then what the output is, right? So now I can go and jump over here. So we'll jump back to IDA free, and I actually want to go into that 548 function and see what it does. And it's actually a relatively simple function. So we'll see, what does it take? So it looks like it takes, whoops, sorry. Looks like it takes, comes in, and there's basically 4 different variables available. Let's see. So we'll go back over here, and I will look at, this was the function call. It puts that string into EDX, and then it put, what's in here, and then what the result was EDX still had the reference to the original thing, but then the value that's the most recent value on the stack, so basically whatever it returns to the stack, is this QUEID thing. So it looks like every time it's going through the function, it seems to be putting EBX into the EAX register, which is interesting. So that might be something that's worth looking into. And also at the beginning of this one, what's interesting is that it called this function, whatever that happens to be, and it put, that would have returned it into EAX, I guess, and then it put that into EBX. And then from then on, it doesn't ever write to EBX. So the other thing too is that this one saves EBX, saves the value of EBX when it goes in here, and then overwrites it right here. So maybe the value at EBX, this one, doesn't change. So I can step through another couple iterations of this and just remember that that's what it is, right? So to make this a little bit easier on myself too, I'm gonna try, oops. Where did I put that? There we go. Did that really fall down there? So to make this a little bit easier on myself, I will also just take a note to myself. Sorry, this is the one I want to go to. 12F 5070. So just take a note to myself that's happens to be the value there, and it's going to call that one, and then it's going to call this one. So that still seems to stay the same. So maybe makes sense because that seems to be a value that's constantly going into that function. Maybe that's where a bunch of this data happens to be stored. So, and you can see, just as an example, this one said net data, and then the result of this was 192.168.150. 129:885. So an internal IP address and port, exactly, TCP port 885. So it happened to pull a couple of names for various components, and then also what I would call the command and control or the remote access address. So because I saved that value over here, this 12F5070, I'm actually going to jump over there and try and see if I can go to that location in memory. So it was 12. So it's actually over here, 12F5070. So it'd be somewhere in this block of memory because this one starts at 134. So this would be my closest assumption. So let us scroll down to that, right? Okay, well, you saw a large block of junk just pass through here, right? So here we go. So 12F5070. So that's right here. So that's what it seems to be going at, is basically the value stored right here, which is another thing that itself is interesting. So the only thing I can say is that what appears to exist here is I should say this 4-byte value, which evaluates to this. Whoops. Say 48 B448. So if I go to this, if I go back to the program, one thing that I can notice, and then this is just, again, I don't entirely know what's going on, but I can make an educated guess here because I happen to run into a number that happens to start with 0048. So I happen to run into a 4-byte number that starts with 0048. So my hypothesis, not based on any context here or anything like that, and if I drill down, this is where it kind of gets to like either I can try and take that whole, exhaustive approach, or I can try and use some of my intuition and guesses about what's going on to guide me. In this case, rather than trying to exhaustively go through and figure out exactly how that number is being retrieved and dealt with, I can actually try just jumping to where that memory pointer seems to suggest I should go. So let me go back to here. So it says 48B448. So if I go back here to the memory map, I can try and see where that happens to be, and that happens to be right here in the code section, right? Yeah. So look at this. And you know what? Let me do this really quick. So it's over here. So let me just get this to be bigger. There we go. So that's actually, you know, way up further, or way up above where the code's executing. So let me, yeah, here we go. I can open it up by double clicking on it, and it'll kind of give me a similar view to what I was looking at before, but it won't just open the window that I was using. So it allows me to basically have a second view into the same block of code that, you know. I'm actually going to go and look at the text content first and see what the text content happens to be at that location. So 4.8. Yeah, 4.8 B4 something something. So you can see that what's interesting is that right here, oops, 4.8 B440. So right around here we end up looking at the code, and we end up seeing that there's like the word mutex here, there's this thing here, and if you remember when we were analyzing the, or I should say when we were modifying the malware, when we were configuring it initially when we tested before, this was one of the empty fields as well. So it occurs to me that there's a bunch of configuration data inside of here, but it happens to be encoded in some sort of strange manner, which I might have to like unravel if I want to. So what I might do is I might continue going down . So that we can see, because I want you to be able to see this stuff. So I'm actually going to try entering the function and see if I can figure out exactly where in that function it starts to retrieve this data from the memory location. So what's interesting is that you can already see that there's a reference to that string in there, right? So let's see. So it saves this value for us. Then it also saves whatever value this is for us. And one of the interesting things too is that you'll notice that this string right here is actually, is actually just like hard-coded in here. So just above this function. So it uses that for some reason. So you'll remember that 48B548 was the value that was stored in that memory address. So this code right here actually has some sort of hard coding or basically right here, right? So we still have the ASCII value install that's stored at EAX, or that's stored, the pointer to which is stored in EAX. So that's 48D684. So and so what I'm basically going to try and do is I'm going to try and figure out at what point in this function it happens to pull whatever the thing associated with that is. So there should, at some point, because I know when this function exits, it reveals a string to us. In this case, that would be the installation configuration string. So I'm walking through to try and figure out at what point in the function that's actually made available. And so this is kind of a nice way of shortcutting some of the maybe more complicated or exhaustive legwork that you might have to do in IDA-free, is to try and figure out basically where in the context of the program it happens to be doing this. So got this value for whatever reason. So there was a question about whether I ever use GDB. I would say that Immunity Debugger happens to be more useful on Windows systems for me, just because GDB doesn't natively interpret a lot of the Windows API and stuff like that. However, I use GDB a lot for various things as well. So what's interesting is it merged this thing with this value here. Oops. And so then finally, it calls a function, this one, which is the last thing it does before it returns. So my expectation is that this function is going to be the one that provides back to the caller, or I should say that provides back to the program whatever, or yeah. Oh, okay. It's a little bit funky here because it did all these things. So it actually happened to do a non-standard return. And then this should return us back to where we came from. So actually this thing looks like it's just telling me maybe an install value or something. I'm not sure. This might actually be a Boolean value to just tell me whether or not to install. So let me go here, combo path. So we'll go back here and try and see if we can pull that data point out. So now we're kind of analyzing the runtime behavior of this inner function to see how it compares to the previous one, which I think at various intervals ended up picking like I think one number that was in string form that was 69, and then another one that was like 890 or something like that, which it then appended to this. So now this one has 6F. So there's this is the one that was 69 in the previous, and now it's 6F. So that's kind of interesting. And then 890, for whatever reason, it's looking for 890, which I believe was the same value from the previous one. So let's see what happens if I kind of go forward with this. So let me look at the other VM and see if I can make heads or tails of what's going on at the end of that function. So we're looking at this right here to try and figure out what the deal is with this one maybe. So the idea here is to try and figure out whether or not we can identify where that code is located, or I should say where those values are located in memory. Right now, doesn't seem to be giving me a whole lot. This one says that it's located at this this location is where it decoded to, but for whatever reason I'm not able to glean how this function became aware of that. So one approach that I could take is I can go back here, I think, and then I can try rerunning that code and see if that ends up helping me out. Yep. So this is one of the nice things about using a debugger, is that I can kind of go back and forth like that, right? So I have this right here. Let's see if I just start going into every single one of these, see if that value ends up being discovered. So this is going to be another function that I'm going to jump into. And so what's interesting about this one is that it actually calls all these functions to go and look into the resources section of the program. So let's see if I go into this, what ends up happening. So that was just like a really quick function. I don't entirely know what it does. But then, let's see. This one basically looks for a particular resource. So find a resource, EAX is actually given EDT path. So there's like an interesting thing there. So let me go over here and and we'll see if, so I've got this resources section here, right? Let me see. I forget if this version gives me the ability to navigate that. View. Anyway, for whatever reason, it seems to be able to be requesting resources, like a Windows resources by name. So it tries to find it. I'm on the call right now, so what I'll do is I'll go to the next one. And then that one says that it returned this value, which is within the program memory space, into EAX. And then the next call is to put that into the EBX register. So my theory would be that that value is going to be maybe an address that has to do with the resource of the program. To try and validate this assumption, I can go over here and I can say, where does the resources start? And the resources start at 4AA. So let me go back here to the CPU, and 4AA778 is the address. So 4AA, let's just go down here and try and see what happens if I look at that in IDA. What was it, 778, I think?
Yeah.
Come on. So what's interesting is here I have this data. I don't entirely know what this data means, right? Somehow this thing might be getting that data. I'm only guessing here because it told the program that it was looking for the resource in a particular location. So it was looking for it in it gave it by name, and it gave it by name based upon those strings that were human readable that you saw earlier. So my assumption is somehow it manages to turn this data into the either reference to or the actual path that we saw earlier, the one that was like msdtc/darkcomet.exe. So what I'll do is I'll go down here and I'll see what happens with this. So EAX ends up, and also it's in EBX, so that points to that pointer. Each module is null. That always means the current program. You can actually have programs that look at the resource sections of like different libraries or other programs that they've loaded. So now I'm going to it's going to load the resource. And so now what's interesting is it's loaded up this really long string value here. Actually, what it did was it gave me, so this is a pretty useful thing. So it gave me an address right here. So what it returned was this address. And that address is 4C60C0, right? So 4C60C0. So you'll see here that's almost similar, at least these 2 bytes. Right, these two top bytes here are the same as the lower 2 bytes of of this one right here. And in fact, C is the same too. So what it really gave us is it gave us an offset in the program memory of where this other hexadecimal string happens to be living. So now, what you can see what we're doing is we're kind of connecting the dots here. So now, what I want to do is go here, right? So 4C60C0, right? So how about if I go, I'm going to first look at that in IDA Pro, right? I mean, not in IDA Pro, sorry, in Immunity Debugger. I'm going to go here. So 4C is actually let me see, 4C, I think it is, I think it's still in the resource section, you're right. So, yeah, it's way at the end of the resource section. So, let me just go ahead and open this up, right? Oops. Six zero. What did I say that was? Whoops. Go away. 4C 60C0, right?
Yeah.
4C 60C0. Oh, you know what? Sorry. So one thing to keep in mind when you're looking through these things too is that two different encodings. So it was in Unicode encoding before, which would hide a lot of the ASCII character strings. So here, this one is pulling up this value. So you'll notice that there's a whole bunch of these, right? So there's this one, which happens to be the string that we're looking at now. And then there's this other one that's right here. And then there's this one as well, which ends over here. And so if you remember, there was like that other one that we were looking at that's right there, and that one right there, right? So, so these are all interesting because they're like hexadecimal values, right? That it's loading up for the configuration, but they're not entirely human readable. So what it's done is it's gotten a reference to it, but it can't read it yet. So we'll go here, size of resource. So it's going to do now, just to kind of give you a kind of, why is this thing, there we go. Just to kind of give you a quick heads up, what it's going to do is it's going to 7,000. Let me just go over here really quick. Whoops. So, yeah, and 7,000 actually just tells it, I guess, where the end of the resource is, right? So, go back here to the CPU window. Some point in here, it's going to decode.
Yeah,
it's going to copy it, yeah, and then it's going to decode it. And I don't entirely know. So here is it putting a reference to that string, which now this one, so this is after it's been copied, it's already been copied here. You can see that now it's pointing to stack memory. Now a copy of that string happens to be on stack memory. So then it's probably going to operate on it in one of these functions coming up. Maybe this one. Or do something with it. So I don't entirely know. Let's see, ESI is that. So let us, yeah, you can actually see it on the stack right here. That's the one. So then what it does is now that it's saved a copy of it, it's got to free the original resource, right? And then finally, maybe somewhere in here, it's actually going to do some sort of decoding of that string. So you can see that, and this is where your stack ends up getting highlighted, or where your stack can kind of show you what's going on. So it highlights, while I'm executing this, what's being referenced by the current code. So this means that this function is actually still working on that data, which is kind of what I wanted to see. So now we'll go and try and see what it decides to do with it. And I'm not interpreting every one of these things. What I'm really looking for here is outcomes that change. So really, this lower right-hand window, what ends up getting put on the stack. This window underneath the CPU view tells me what the immediate variables are doing, as well as the CPU state here on the right-hand side. So there's a loop in here that it happens to be, that it looks like it's executing. Oops. And then returns. Let's see what this does. So then that returns, and then this returns. But not before so it's putting all these things back into the different registers. Just trying to see if I could catch the, and I think I missed it. Oh no. So you can see this one's still referencing it, and I might end up having to end this before we get to the bottom of this one. And the goal here is just, you know, my assumption, my expectation, just based upon what I've seen so far. And kind of what I'm doing is I'm digging further in. So you'll notice that I've kind of been alternating between using the step into to go into functions. And then once I get to a certain point where I want to stay within that function and see what the inputs and the outcomes are, mainly what's still, my goal here is this value is what it pulled out of the resource section. So this value, I've theorized at this point, contains the information telling the program to, telling the program to use that path, the msdtc/darkcomet.exe. So that information is in this string right here, but it's not a simple translation of these hexadecimal values into ASCII. There's some sort of encryption routine at play here. And my goal would be to try and find out what that encryption routine is and where it's located in the code by following the different paths this way. And so that's kind of the iteration, or the, like, you know, the systematic approach I'm trying to work with here is I identified a place in the code where I didn't have a lot of information, then, or at least I had input information. I had a key request, right? And then I got a value out of that. And there was a function that was called between those two boundaries. So then I drilled into that function and I worked through it, trying to see if I can narrow down to where the, to the point where I've now gotten down to where it retrieves the intermediate value. And I've managed to tie that back into the raw data that's on disk. So now I'm trying to narrow down to the functionality now that I know where the raw data is, and I no longer need to know the key. I need to figure out how it gets from this raw data to the decrypted value or to that path, right? And that's kind of the systematic approach I'm going to do is eventually I'm going to work down to a point where I get to the code that has the encryption key as well as this value. And the output of that function is going to be some value y, which is going to maybe be that, maybe it'll be that, that path string, or maybe it'll be something else.